The paper of the day is Implementing Data Cubes Efficiently. Business intelligence and analytics use cases involve complex queries on potentially very large databases. To minimize query response times, query optimization is critical. One approach to optimizing query response times is to pre-compute relevant values ahead of time and to use those pre-computed results to answer queries. Unfortunately, it is not always feasible to pre-compute every potential value that is required to answer arbitrary queries. This paper describes a framework and presents algorithms that pick a good subset of queries to pre-compute to optimize response time. A data cube is often used in business intelligence applications to present multi-dimensional view of data that can be explored to find values of interest. Within a data cube, each dimension represents an attribute of the data and values at each cell the measurement for that set of dimensions. Data cubes are commonly used to describe time series data, allowing a user to view dimensions of the data at different points in time. By cleverly choosing what parts of the data cube to pre-compute or to materialize, we can reap dramatic performance benefits. Summary cells in a data cube can be represented by a value of all for a given dimensions. A cell in the cube with an all value for an attribute represents an aggregation of the data along with the attribute of interest. Any cell that has an all value as a component is called a dependent cell. Its value can be computed from those of other cells in the cube through aggregation. The data cube. As an example, we can imagine database with 3 dimensions: part, supplier, customer. This data can be grouped in 8 different ways: part, supplier, customer, part customer, part supplier, supplier, customer, part supplier, customer, and none. The primary contribution of this paper is to recognize that this data can be organized as a lattice where queries that can be answered from other data rest above the data in the lattice. A lattice view of the part supplier customer database. Consider 2 queries Q1 and Q2. Q1 is dependent on Q2 if Q1 can be answered using only the results of Q2. This dependence relation implies there is a path downwards from Q2 to Q1 in the lattice arrangement of the data. Optimizing data cube lattices. Given these observations, how can we optimize queries using a lattice? This paper presents a greedy algorithm for solving this problem. The greedy algorithm assumes that each materialized view comes at a cost, assumed to be the number of rows in the view. Given these costs, the greedy algorithm attempts to select a set of views S that minimizes cost. Another way to define this is to look at the benefit of adding materialized view to the set of views already materialized. If the newly added view improves the cost of evaluating other views, then we can add that view to the set of views materialized. This can be codified by a benefit function P that computes the benefit of adding view V to the set of view S. The greedy algorithm can be summarized. So here we look at the high-level greedy algorithm. S equal to top view from I1 to K to select view not in S such that P is maximized and S then union V with S. The paper goes on to prove that greedy algorithm is always within 63% of the optimal solution for all lattices, providing a guaranteed range of performance optimization by applying this technique for selecting materialized view.